Great. So, thank you for this very warm welcome and for the nice introduction. And I think this is a very new topic for everyone here. And I completely trust Mustafizu for helping you out with the basics of quantum computing. Having said that, let me make it very clear, it's not an overnight thing. What everybody is doing in the name of faculty development program, we are just trying to give you a glimpse of this beautiful whole field called the quantum computing. To say that we can do justice to this whole idea, we will be unfair to it. Nobody can teach you quantum, not even if Richard Feynman comes down and drops from heaven. Not even him, whether it is Richard Feynman or whether it is Albert Einstein. No one can do that, at least in the time frame which has been awarded to us. I mean, I have been into this field for, I would say, since 2012, and I'm still learning. And it's every time I read something, I still feel it is such a new. This is new. This is something that I've read for the first time. So trust me, it's not a new field. And if whenever and whatever point you feel disgruntled or disappointed, I'm sorry. I'm sorry. So whenever you feel disgruntled about that, this is very difficult and it's disappointing to you, you get frustrated, trust me, accept it, move on and finish it. There will be many explanations to a separate single thing, because when we talk of quantum computing, we talk about a field which is as small as an atom, as an electron, as a photon, and nobody has seen them. So it's just an imagination. So you have to let your imagination run as wild as you can. So if there are things which you think are weird, you should just accept, rather than analyzing and counterintuitively using your logical brain that how is this possible. This is possible because this is quantum. So sometimes that discontentment was going to be there, but I just trust it and move on with it. So essentially, I was given the task of explaining how electromagnetism fills into the space of quantum computing. And I will be covering broadly certain topics. And I don't know, again, I will say that I will be able to do justice to each of them in that time frame. But sorry. I'll try to do best I can, right? So electromagnetism is not a new concept. It's been there for a long time, right? So if I say how electricity and magnetism kind of evolved, I should look on at it from the historical perspective, right? So electricity and magnetism were somehow somewhere written in the early Greek literature as something two very distinct quantities. So electron was something when you were rubbing fur against amber or things like that, and they found that there was a very interesting phenomenon happening. So when they rubbed this rod with amber rod with some kind of dry leaves or something, they found that with fur, they thought they saw that something got attracted. Dry leaves were getting attracted towards it, and this was what they conceived as electricity, right? So it was a different phenomena, right? So electricity to Greeks was different phenomena, and for them, magnetism was a magic that was encapsulated in special stones called the lodestones, right? So lodestones were those magical stones which would attract iron particles towards it. So for Greeks, electricity and magnetism were two different quantities. Fast forward to 1600. Now there was this famous physicist called Lord Gilbert, and he was with the Queen. And he gave a very interesting phenomena. He said that our Earth is a giant magnet. And this is how he explained the concept of magnetism. But now again, magnetism and electricity was different. So Gilbert said, okay, magnetism is what can be described by a Earth, imagining Earth as a very, very giant object, right? Next came Benjamin Franklin. Now, Benjamin Franklin was somewhere around 1800. I'm not very sure about the year, but somewhere around that time, right? So, what did Franklin do? Franklin carried out his famous kite experiment, right? And what did he prove with it? He proved that the thunder, the lightning that we saw was nothing but a discharge of electric charges, right? So, did he do that? There, he basically did the marriage of an experimental subject, that was electricity, with the naturally occurring phenomena as giant as light. So he actually kind of combined both these concepts and brought into one particular concept called the electricity phenomena. Again, electricity was still electricity and magnetism are still two very distinct quantities. Next came Coulomb. Coulomb, what did Coulomb did? Coulomb explained, he gave a beautiful mathematical explanation to electricity. What did he say? That okay, he gave this very interesting he gave a formula where he said that K Q1 Q2 by R square, and he unified this with the Newton's gravitational theory, right? So he expressed that okay, the
Sorry
force
for
between
interrupting,
two.
ma'am, but it seems you are writing something, but we are not able to see it.
Oh, how
Uh,
come? How is that possible? You are not seeing my screen.
so we can see your screen, but it's blank. Means it's maybe you have
Just the screen.
mistakenly shared the window, not your entire screen. So maybe you can stop sharing and share it one more time. So then maybe.
Okay, I'll do that again. Thank you for telling me that. Wait. I'm so sorry. I'll try and do that again. Can you see my screen now with red something written? Hello?
No, 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 ma'am, no. We can
Oh
just
God.
see EICT Academy MNIT Jaipur only. That is, your screen is somehow
You are not
shared, but we can see all the
uh,
tabs open. But yeah, what you are
you are
writing
not
is
able to
not.
see my PPT is also not visible, is it?
No, no, it's not visible.
Oh my God. Should I go
So
about it?
maybe you can click on stop sharing.
Okay. Wait. Uh, wait. I have to stop mirroring first. Okay, a second, please. Sorry. Why is it not
So
coming?
ensure that you have shared the entire screen, not a particular window. So maybe that can be a reason.
Huh?
Um,
I should
if
say
you
stop sharing.
after stop sharing, once you click on share content button,
Share.
which is share button, so then
Uh-huh.
you will see the first option of screen or application. So ensure that you have selected that option only, where you have selected the entire screen, not any particular window or something.
Okay.
Because if you
Sorry.
select some window, then only that particular window will be visible throughout the session.
Oh my goodness,
For
that is
example, if you
something
have
I did.
opened Word file and if you have selected that, so then it will remain like that for the entire session.
Oh my God. I'm so sorry. So sorry for that. Now can you see my screen, which is written EICT Academy MNIT, right?
Yes, yes, yes. But you have to switch to the correct tab where you
I'll
are
do it.
writing. So then only we'll be able to.
Give me a second. Give me a second, please.
Right, sure, sure. I guess you are mirroring your iPad on this, right? So
Yes,
that's yeah.
yes, that's what I was trying to do. Okay.
So you have to ensure that that iPad screen is also open. So now we can see your iPad screen. Yes, yes, it's visible now.
Now you can see, right? Oh,
Now it's
thank you.
visible.
Now
We
you
can.
can speak.
Yeah, yes, yes.
I'm so
Now
sorry.
we
Should I
can see.
repeat? Or is it fine? Huh?
No explanations. I guess people have understood it. Maybe you can just
Yes.
briefly outline
It's
in one
just a
word what we
history,
have.
historical. It's just a
Uh,
historical walkthrough.
yeah, sure, sure. Thank you.
So I will continue. And thank you so much. And sorry for all this. I'm so sorry. Okay.
No
Now we
issues.
come up Coulomb's law, and then Coulomb gave this very beautiful law, where he basically related the force between the electrostatic force with the famous Newtonian's gravitational force. Right. Electricity and magnetism are still two different entities. Now came Oersted in 1820, and voila, that was one breakthrough. So he was doing some lab experiment and he was showing some experiment to the students. And what he realized was that whenever current passed through a coil, there was a magnetic needle placed very close to that coil, and suddenly the magnetic needle would start fluctuating. So when he tried to repeat this several times, every time he realized that whenever the current passed, there was this fluctuation of the magnetic needle, right? And when he realized, for the first time, he realized that change in electric current gave rise to magnetism. And this was the first time when electricity and magnetism kind of came together. And this was by the famous Oersted's experiments. Then came Faraday, and based on his theory, he thought, why not? Let me try the other way around. And what Faraday found out was there was a similar reaction, similar behavior when there was a change in magnetic field. So a change in magnetic field would give you rise to electric current. So Oersted and Faraday basically laid down to the famous explanation given by Maxwell's theory. So what was Maxwell doing there? Maxwell basically unified the concepts which have been developing over the years and came up with the famous classical Maxwell equation. Now, if I have to tell you all these equations, I'm pretty sure you all have learned them in your standard 12th. So this is nothing new that I'm going to come up with. These are very old equations and all of us are very aware of it, and they form the bedrock of complete electromagnetism. And I need not say how wonderful and beautiful these equations are, because these equations have basically formed the foundation of our being in principle. So just to summarize, the first law is a Gauss's law of electricity, which states that electric charges produced electric fields. Next is the famous magnetism law, which it says that magnetism cannot exist in poles. If there's a north pole, there has to be a south pole, and magnetic lines are always closed loops. We know this concept. Then came the Faraday's laws, and of course, Faraday's law states that change in magnetic field would induce electric fields. And then the famous Ampere's Maxwell law, which says that currents and changing electric field would produce magnetic field. These are the very basic laws of Maxwell equation, and as I say that there are many lot of phenomena is that we know today is basically based on this. The classical electromagnetic insight basically lays down the foundation of several phenomena, and one of the most important and most interesting output of electromagnetism is light. Using electromagnetism, we could explain what light is. So light is what? Light is an electromagnetic wave. It travels with the speed of light, which was mathematically proven to be this value by the use of the famous Maxwellian equation. So we see that Maxwell actually provided us the first theoretical identification of light. Basically, he brought optics, which was a concept that was introduced by Newton under the umbrella of electricity and magnetism together, called electromagnetism. Right? Next K comes, where lies the success of Maxwell's electromagnetic theory. So, of course, Maxwell's theory is giving us the propagation of these waves, whether it is in air, whether it is in metal, or whether it is dielectric. All devices that we think today and things which have made our life easier, whether it is a transformer, antennas, waveguides, propagation, Wi-Fi, internet, whatever we think about today is actually an output or a key application of classical Maxwell's electromagnetic theory. Technologies that we use today, whether it is MRI, whether it is CAT scan, whether the smartphones that you're holding, they're all an application of electromagnetism. Now, something that could not be, explained using the classical EM theory. So these laws, these phenomena become very important because for them, we needed an explanation. There were questions that why, if light is a wave, why is this thing happening like that? So okay, so what were these three principal phenomena? Though there were many areas where classical EM failed, but those, I'm trying to just clarify, just through an example, I'm just trying to tell you three underlying basic phenomena which actually kind of shook the whole scientific community, which was rooting for classical electromagnetic theory. Now, these three phenomena were the black body radiation, the photoelectric effect, as well as atomic spectrum. The black body radiation, also known as a UV catastrophe. So, this, as per Rayleigh-Jean's law, they say that at higher frequencies, the energy would tend to infinity. Is it true? No, it is not. Of course, there is no phenomena in which the energy would reach infinity. What it was classically observed was that the energy would keep on increasing as in intensity, and at that another point, it will again start increasing. So this was one basic phenomena where the black body radiation, where classical effect. The second was a photoelectric effect. Now, the photoelectric effect, as perceived using classical EM theory, was that if you keep on increasing the energy, you will get to see ejection of electrons. That means ejection of electrons has nothing to do with the frequency and everything to do with the energy that is being impinged upon it. But is it true? No, it is not true. Because what was observed was that irrespective of the intensity of radiation that was falling on the surface of a photoelectric material, the particles will eject only after a certain threshold of frequency. It has nothing to do with the intensity of radiation that was falling over it. The third phenomena was the atomic spectra phenomena, in which they would say that, okay, since the electron is spinning around the nucleus, it should eventually collapse inside the nucleus and in the process give out continuous spectra. Is it true? It is not. Because what was observed was discrete spectral lines in case of hydrogen atom. All these phenomena made scientists sit and think, why are these things deviating from these electromagnetic theory concepts? And thus came the breakthrough, which was given by the famous quantum theory. The first breakthrough was given or explained by Planck. And the Planck was the first person who basically, he can be said to be the founder of the quantum theory when he gave a very famous equation where he said E is equal to h nu. And now this is kind of, everybody knows about this equation. At that time, it was very new, and basically he gave the concept of quanta. That means energy exists in small packets called quanta. And now energy, which was so long being considered as a continuous thing, suddenly becomes quantized, suddenly becomes packets, suddenly becomes small discrete quantities. So this is for the first time that Planck gave the concept of quanta. Next came up Einstein. Using Planck's theory, he explained that light again is not only a wave. He said that light is photons. What are photons? Photons are nothing but quanta of light. That light exists in small packets of energy, and these he termed as photons. And using this theory, he was able to explain his photoelectric effect, for which he was awarded Nobel Prize in Physics. Right? Next came Bohr, and we know why Neil Bohr is famous. Neil Bohr is famous for his famous atomic structure. He said that there is nucleus in the center, and electrons are rotating around it in discrete energy levels, which, as of course, we know are called orbits. So he discretized and he said that the electron has to jump from one energy level to another energy level. It should have discrete energy or discrete quanta of energy should be impinged upon it before it to jump from one shell to another or from one orbit to another. And thus explaining the discrete spectral lines which was an anomaly till that point. And finally, here was Paul Dirac, who basically gave us the very famous quantum field theory of radiation, and which actually saw the birth of the whole phenomena called quantum electrodynamics. Another framework which describes how photons and electrons behave in quantum field. So what is quantum computing? Quantum computing is nothing but a marriage between the classical EM theory and the quantum electrodynamic theory, which developed over years by scientists such as Feynman, Einstein, Planck, Bohr, Dirac, Schrodinger. So all this marriage or unification of two concepts is quantum computing. And I will tell you how quantum computing is a marriage between the two things. So we know qubits, like Dr. Rahman mentioned you today. What are qubits? Qubits are nothing but a way of expressing your quantum states. And quantum states we know can be expressed as Ket0 and Ket1. Unlike a bit which is expressed as 0 and 1. So this 0 and 1 is simply what? A normal classical state. But what is this? This is a quantum state. So this is going to follow the principles of quantum mechanics. They are bound to follow, and they would come under the purview of quantum electrodynamics. Next, we think, sorry, give me a second. Next, we talk about photons. Photons, as Einstein mentioned, were packets of light, which means they can be used to represent quantum states, and which is why photons become very interesting when we talk about realization of qubits, whether it is in the form of photonic qubits or whether it is in the form of spin qubits or any other form. So photons are extensively used to realize quantum states. Besides, photons are extensively also used when we are talking about control and readout operations of these different quantum states. And sometimes photons are referred by a very interesting name called as the flying qubits. Sorry. Now, why is classical electromagnetic important? When we talk about engineering of these quantum hardware, whether it is the pulse that you are sending to your system, or whether it is a retrieval of these quantum states, whether it is how you're building the chip, basically the quantum processing unit, or whether how these gates are manipulating, all of them are still governed by what we know as a classical electromagnetic theory. Cavities, waveguides, resonators, circuits, RF pulses, electromagnetic pulses, all this is still governed by the same classical EM theory. Therefore, I told you that it is the magic of quantum computing lies as long as classical EM and QED are in kind of a superposition. The next is QED as a deeper theory. Ultimately, QED will give you a microscopic explanation of any objects, of any interaction between the qubits. So whether it is a spontaneous emission, absorption, exchange of photons, or whatever, be the coupling, etc., all of them is explained by the QED theory. From this point, from this I come to the point why quantum computing becomes important for us to know, for us to study, for us to be motivated enough to, I mean, I'm pretty sure many of you sitting here would be curious why the hell I'm doing this if classical EM still forms a bedrock of all the quantum computing technologies that are existing. So here are a few advantages of the quantum computing. So they explore multiple possibilities. I'm pretty sure when Dr. Rahman spoke to you about the concept of superposition, he must have mentioned that it is possible using quantum mechanics that we can explore multiple possibilities simultaneously. Then we can tackle intractable problems which cannot be solved classically. I mean, classical using classical theory, you can never solve them. But those problems can be solved using quantum computing because of the inherent properties of superposition and entanglement. Superposition is helping you explore multiple possibilities at the same time, when entanglement is giving you the option of expressing the correlation between these different states. And when you explore the correlation between two states, you are basically reducing your solution space to a very small value. First, you are exploring so many possibilities, and now using the principle of entanglement, you are reducing your the whole space into a very small domain. And then comes the concept of interference, and using interference, you make measurements much easier at your end. So these three phenomena, I'm pretty sure Dr. Rahman has explained to you. I'm just trying to reinforce this concept here, that using these three principles, you are able to take out the advantage of quantum computing in your vis-a-vis the classical computing. You can build encryption which can never be broken, and unlike the RSA encryption, which people think that using quantum, the large factoring problem can be solved, and of course your RSA encryption will fall flat, and thus we are talking about PQC, that is a post quantum cryptography concept. Then we talk about optimization in logistics, such as the traveling salesman problem, where the salesman has to move to, say, cities A, B, C, D, and so on and so forth up till X. And now if your salesman has to find out what is the most optimum way of, so that I can travel to these different places, and I can do this most efficiently, and at the same time I efficiently in terms of time, and also both in terms of financially, that the output should be maximized, and his personal input in terms of traveling to these different places also gets minimized. So this is the traveling salesman problem, and usually used for problems such as logistics and supply chain. All these problems can be solved using optimization and logistics using quantum computing, again because of the same principle, that we can kind of manipulate several possibilities at the same time. Then, of course, climate modeling is a basic requirement currently. Then we talk about computation speed. We talk about how quantum machine learning can be ingested into the current race of AI and machine learning, and how we can explore multiple possibilities simultaneously and make the system faster and more efficient. You want to harness entanglement, you want to have personalized medicines, and then you want that your current encryption codes become very strong and they cannot be broken any further. And this is what we talk about. As I mentioned, post quantum cryptography. And then you talk about how you can speak in multiple languages and maneuver your data in different languages. Looking at this, we can basically say that quantum matter and technologies and quantum computing can be basically spread around these three domains. Um, the first is these novel quantum technologies, where we talk about how we can decipher the different quantum states. This actually encapsulates the different quantum hardware, how we are exploring the different quantum hardware. Uh, and now, of course, topological qubits is on top of it, because these are something which are exotic and people are still very curious about it. And it is a very novel quantum technology and is being pursued by Microsoft at the moment. And nobody knows how it is and what is it working at. But if it works, it's going to be beautiful technology. Then we talk about technologies such as quantum sensing, we talk about electronics, and we talk about phenomena called spintronics. Again, spintronics is a very interesting phenomena, um, which is currently being explored by academia at different levels, including my PhD supervisor. Then comes the other domain where we talk about applications of quantum computing. Of course, as I mentioned, top on the list is optimization. Then we talk about machine learning in quantum domain, also often known as quantum machine learning. We talk about the factorization problems, in which it is assumed that using quantum computing, you can factor using the Grover's algorithm. You can factor very large numbers and come and be able to break the RSA encryption, which is a current encryption technology. You can also do search problems. Just a very simple example to explain how search would work if we are able to, scale up our quantum hardware. So imagine if you are given the name of Mr. XYZ. Supposedly, if you're given a dictionary and you're asked to find out the number of supposedly my number, you will, Vichagoyal, you will go to R, and that is how you will do the search, right? Searching is not a big deal in a sorted array, right? Even in unsorted array, you can do the searching of Vichagoyal will not be a difficult problem. But what if I give you my number and ask you to do the reverse search, ask you to find out the name corresponding to a particular number? Do you think it is possible using the current algorithms which are available classically and on the current classical hardware? I don't think so. Not in the time frame of Earth's life. So using quantum algorithms as of now are such that you can achieve these search problems in an unsorted array easily, the reverse kind of problems, right? So that is one NP hard problem which you can do using quantum computing. Then is a simulation problem. So here we talk about the non-equilibrium dynamics, we talk about finding out superconductivity, we talk about quantum chemistry solutions, where we are basically trying to find out the ground state of any atom or stuff like that. And we talk about the topological systems, we talk about the quantum field theory, we are talking about open quantum systems and high energy physics. We also talk about discovering new materials such that we can discover new, say, superconducting materials, right? Now, these superconducting materials will do what? They will discover new materials which will speed up the building of new quantum hardware. So it's like a loop in problem, right? You come up with a better algorithm, The algorithm will give you better material. The better material will give you new hardware, and this new hardware will help you back in developing better material, discovering new materials, and so on and so forth. So it's like new algo corresponds to new material, corresponds to new hardware, and again you come back to the new algo. So yeah, this is how the loop can work and help you scale up this particular issue. So now here is a layered architecture of quantum hardware. So right at the bottom is the physical quantum processor unit. What do you mean by physical quantum processor? Basically, the quantum hardware. Now, this quantum hardware, I had very briefly touched upon it on day one. And in this particular hardware, it can be anything, right? And the first layer is the quantum hardware called the physical quantum processor. Then you talk about quantum error correction layer. Now, whatever the hardware that is available can basically manipulate certain number of qubits. Say it can manipulate, say, X number of qubits, right? But the answer or the result that you get out of these qubits is faulty because you have not accounted for the error in this. So what you need here is, if you have, say, bits 0, 0, 0, 1, you want to append it with more number of bits, something that is currently done using in classical computing, and then make this whole system more immune to noise. So this is what you would call is your physical qubits, this whole number, and this whole, sorry, and this whole digit together will be called what is called as the logical qubit. So I'm pretty sure you have heard of these two terms quite often. We talk about physical qubits and you talk about logical qubits, right? So here is the concept of physical qubits. So what you do, whatever the state you have, you pack it up with more qubits, make them more immune to noise by using special algorithms. And then after packing this, you are basically making them fault tolerant. And then what you get is a logical qubit. Clear, right? Now, this is known as a quantum error correction. And this is something that the scientific tech community is not able to achieve as of now regarding the quantum technologies. That on top of it lies a quantum algorithm part. This is essentially the heart of the quantum computing technology, basically. How you are planning your how you are planning your workload is all dependent upon your quantum algorithms as they are. This includes the very basic algorithms, the Shor's algorithm, the Grover algorithm, the Bernstein-Vazirani algorithms, and so on and so forth. But since you still don't have a logically correct quantum processor, we are still far from implementing these algorithms. So what are we currently doing is, we are currently in an area which is known as NISQ, near-term intermediate scale quantum computing, where we are saying that the solution that you're getting, where the readout that you're getting or the result that you're getting has a certain level of correction, has a certain level of deviation from the real result. The error is not 100% correct, but using probabilistic measures, you can say, okay, the probability that this result is correct is 80%, and maybe 20% is the chance that this result may not be correct. So we are at that stage. And we talk about something known as error mitigation. So we are still playing with quantum technologies here. We're talking about error mitigation. So we are still in that NISC era, and the day we are able to do quantum error correction, your physical quantum processor will move to this layer called the logical quantum processor. And using logical quantum processor, you can efficiently implement all your quantum algorithms and do whatever you want desire. Between these layers, you see that there are these controls and readouts, right? These are like the heartbeats, and both these here and here are electronics. Again, I would emphasize these are classical EM. So you see how the whole stack of quantum computer is built upon, right? Should I take a break for taking few questions? Hello? Hello,
Yes,
am I
ma'am.
audible?
Yes, ma'am. You can take the break.
Okay, yeah, please go
You
ahead.
would like to
Can I get
answer
a
the
last
question?
message? Yeah, please carry on. If there are questions, please, I mean, can one of you say, because otherwise I have to disconnect the screen again to go back to the chat screen. Can one of you just say the questions? Or should I mean, what should I do?
I'll read it for you. 1 minute.
Mm, Because, wait,
Starting from okay, quantum error correction is done by classical algorithms, right, ma'am?
no. Error correction is a different field where we talk about scaling up both in terms of hardware. I mean, how these different qubits are interconnected, basically the coupling map of this. And of course, we talk about quantum technologies in such a way where the results that you get uh, is logically correct. So you're talking about having more number of qubits. In principle, error correction is not any kind of standalone algorithm. They are something known as a LDPC or surface codes, which people, of course, they are the algorithms which are going to be implemented, but these are not classical algorithms. These will make use of hybrid algorithms, including both quantum as well as classical algorithms. Yeah. Next question.
Yeah. Next question. How do you look at data privacy and security in quantum scenario? You mentioned giving a number and finding a name.
Okay. I don't think so. I'm in that position. I've never thought about this aspect. So, if your number is, I would just think it logically and say, if you have put your number on the directory, that means you don't have privacy towards it, right? If I have put my photograph on the Facebook and somebody has a look at it, then I don't have the right to say that okay, was private data and you dare not see it. So that's my reply to it. You better not put your better not put your phone number on the directory if you want that level of privacy. Thank you. Next question.
Yeah. What is the difference between logical and physical qubits?
Okay, this is something that I was trying to explain. So physical qubits is how you are seeing your how your basically qubits are currently situated. Physical qubits are basically which are not error corrected. In simple terms, qubits which are in the current domain of physical qubits, because these are not corrected. The day the day when these qubits get error corrected, then those qubits will be known as physical qubits.
Yeah.
Next.
Can you suggest some applications in economics and finance?
Of course, they are portfolio optimization, and there is a whole field known as quantum finance where people are trying to. I think portfolio management basically there's this prediction concept also, right? In economics and finance, where we talk about portfolios, we talk about how something is going to look like maybe a month after, or maybe 5 months later. So all this comes under the purview of quantum finance. Something like you are doing the prediction model. So why quantum computing has an advantage over the classical computing is because of the concept of entanglement. You see, the way data can be correlated using classical computing is very limited. And as your data increases exponentially, classically it is intractable, right? So, however, because of the inherent property of quantum computing using of entanglement, so you can basically correlate multiple huge data together, and which is probably can help you predict. Prediction is one thing where you can do, and second, as I said, portfolio management. Yeah. Next question.
Please explain the error correction concept.
Quantum error correction. Okay, this is not a simple concept. I think you need to have a separate complete session on it. Perhaps I'm not an expert at it, you would say.
Quantum computation time, we'll take it. Okay. Yeah. Ma'am, how sorting can be done?
Sorting, classically, you know how it is done, right? Classical sorting, you know, there's these binary sorting, sorted array, unsorted array, right? Right. But how you are doing, why would you need, first of all, why would you need a quantum algorithm for sorting when you have a classical algorithm already in place for it? That's my question to the person who asked it. So if you have something which is already working on the classical side, why would I need to do it using quantum, right? If you have numbers from, say, from numbers x to y, and you can do it using classical, why would I need a quantum algorithm for it? I don't need it, and I will not do it. Yes, but if I talk about searching, that is a different phenomenon. And I believe you would have a session on quantum algorithms in which probably they will explain how how searching would be done using Vogel's algorithm. If that is the question.
We'll have that. We have a full course also, Quantum QT-05. Some of the lectures.
Probably you will cover that aspect.
Yeah. Do we use binary? Sorry, can you repeat the use of controls?
Control is simple. Control electronics, how you are sending the signal. So whatever hardware, however you are sending the signals, I mean, if you have to manipulate a certain quantum state, you need to send a certain signal. Now, this signal can be an RF pulse, such as in the case of superconducting qubits, or supposedly if I'm talking about technologies like ion trap, or if I'm talking about neutral atoms, or maybe photonic qubits, spin qubits, whatever. In all that case, you can be using optical pulses such as lasers, etc. So essentially, depending upon the hardware technology that you're using, you would need these signals, right? I mean, there should be some triggering force to change a state from ket0 to ket1, or to do some manipulation. Say you want to inverse ket0, right? Just like a NOT gate. So if you want to inverse ket0, you again need some kind of pulse. So that is a control. And when I talk about readout, that I did some manipulations, right? I have a state X and I moved it to state Y, and then I moved it to state Z. And I want to know that after doing all these manipulations, what is my final state? Now, this is a quantum state, right? So quantum state is, as been already explained to you, is in a superposition state, right? Which means there's this probability that it is 0 and this probability that it is 1, right? So, and now I want something where I can, after all these manipulations, want to know what it is exactly, whether it is 0 or 1. So that is what we call is a readout. So all this thing is done using EM pulses, like readout. So how will you read out? You will shine it with light, or maybe impinge a radio frequency pulse, and then based on how those the output and the result is manipulated, how they are interacting, based on that you will get to know what your final output is. So in principle, when we talk about quantum computing technology, building of a quantum state and the final state is a classical situation, right? In between, everything is quantum. So initial state and the final output is a classical. So ultimately, you are ending up in a classical state, because something with probability this and something with probability. I mean, when you're flipping a coin, the coin, as long as it is in the air, it makes no sense to you unless you put it and tap it on your palm and find out what the value is. So ultimately, you want to read that value after all that manipulation. Now, whether you're flipping the coin inside water, inside honey, or inside in the air, or in maybe the outer space, the result is going to be different, right? And which force you are flipping, it is also different. So all these scenarios are going to be different. And if it is now exerted upon by, say, some kind of this coin is your magnetic, and it is it maybe faces some kind of magnetic field, the result is going to be different, right? So ambience is going to be different, but ultimately what you want is to know what happens at the end of the flip. So this is, if I can explain to you what a readout and what a signal is. And control signals is just controlling these pulses. So what actually happens is, you have qubits, and then you subject them to, maybe wait. What I'll do is, what happened? Oh,
Slide is not visible.
okay, wait. Okay, I just wanted to add a slide to this so that I can. Okay, I'm not able to do this here. Anyways, I can't help it much.
Insert between the slides on the left hand.
It is not happening.
Okay. No. You can click the mouse between the two image. I mean, the left
Okay.
column. Somewhere in between, you can click and it. There you can. In between, you can click and say enter.
On a laptop it is much easier, but here
Okay. Yeah, on the laptop it's easy. Yeah, maybe you can add at the end. I think that will be better, and then you can come back.
Okay, I can do that. It is not giving me the option of new slide.
Yeah, maybe towards the end you can explain this question. I think we can.
I'll try my best.
Conventional computers, hacking is possible with the help of quantum computing. Encryption is possible or not?
Can you give again? Sorry.
In a conventional computer, hacking is possible.
Okay.
In a quantum computing environment,
No,
encryption is possible.
No, it is not, because the way current protocol that we are using for cryptography is very strong. Of course, there is a certain limitation, and that limitation is on the physical side, essentially the quantum hardware side. But because it's of the native nature of this technology, hacking is not possible. Because I tell you why. So remember, I just mentioned you briefly that whenever you measure your qubit state, it collapses into a classical state, right? Alpha ket 0 plus beta ket 1 would eventually collapse to either 0 or 1, right? So whenever you're hacking, your state that you're getting is, first of all, the state that you retrieve after hacking cannot stay in the quantum state. It will collapse into a classical state, which means if there's Alice and Bob, if there's transmission happening between Alice and Bob, then the moment Eve drops in and does that uh, measurement, this quantum channel will collapse. And you will know immediately that there has been an eavesdropper. The second reason is that quantum states cannot be duplicated, right? So again, if there's a channel A between A and B, Alice and Bob, and if you have a quantum state running between them, then you cannot say, okay, the quantum state should run as it is, and I duplicate this signal and get it for myself. Again, this is also not possible. So these are the two reasons why quantum communication is hack-proof. That's
Yeah. Last question. QDIT, one with the T. QDIT
Huh?
is a
okay. You did quantum.
QDIT. Yeah. Higher dimensional version of qubit.
Yeah,
Is there any
yeah.
physical realization? Is there
Is
any
there any
physical
physical?
realization?
I don't think so. Though in, I think, NV Center Technology, they say that they have 3 states: ket 0, ket 1 plus, and ket 1 minus. But even in that, they would use only 2 states. So in NV Center Technology, you have this ground state and you have 2 excited states. But you use only one of these. I don't think so it has been realized so far. Forget about quantum qubit. Even in classical, we're still stuck with bits, right? Though you could have done more than bits, right? You would have 0, 1, 2. Besides dimensionality, I don't think so there's a huge advantage to increasing your base from 2 to anything else. I mean, that's my personal opinion. I'm really not sure about it, if I'm right or wrong. But I do, of course, the physical realization has not been possible beyond the qubit. Is that
Thank you.
it?
Thank you, ma'am. That's all. Yeah.
I'll get a glass of water if that's convenient. I'll just be back in a while. Is that fine? Hello?
Yeah, ma'am. Take your time. Yes.
Yeah, thank you. I hope so far it's been good, and I was able to explain some basic concepts about this. The technology part I had covered briefly in my first session, and since this is not a dedicated quantum hardware session, I will not again do a deep dive into this. But this particular slide is here to show you how classical EM, classical electromagnetic theory, is very important when we are talking about quantum hardware technologies. I've briefly given an overview how qubit is a quantum state and how readouts and control signals need to be classical. So here I will just cover the different aspects one by one. So we know superconducting qubits. Superconducting qubits, the basic basis is Josephson junction, and Josephson junction, is nothing but a non-linear inductor. This is what I had explained there in my first session. The control mechanism is the microwaves and EM circuits. And of course, these gates are fast. And of course, these are the gates. This is a technology which is most widespread at the moment. It is currently being pursued by IBM, Quantum, Rigetti. And then it has its own fallout. It has very small time of coherence, which is basically some microseconds. The second technology which is pursued is trapped ion technology. It is again used by, it is being commercialized by a company known as IonQ. and it basically uses ions in the EM field, and uh, to confine ions in a specific position, to change the state of ions, to do some manipulation of these ions, whether it is interference or superposition. We use lasers, radio frequency traps, etc. Advantages are that um, they have long coherence time, they are high fidelity, but more immune to noise. But okay, complexity, and of course, since the lasers that are required here need to be very, very precise with very small FWHM and etc. So this is another limitation for IonQ. Another advantage of this is almost at room temperature. By room temperature, I mean something around 50K. Then there is this neutral atom technology where we use atoms and you use optical tweezers to move them around. Again, implementation or control is done using lasers or Rydberg excitations. It is naturally identical. We have scalable arrays. Again, the drawback is, or maybe the challenge here in this technology is requirement of very highly precise lasers, which is still an important thing and a limitation. Then we talk of photonic qubits. These are extensively used in technologies such as quantum communications. And in this case, we use single photons. Now using single photon generators. You are using technologies such as beam splitters, detectors, optical fibers for its mechanisms. The problem here is that not just they have good, sorry, I think this is incorrect. They have very good coherence. The coherence is very good, but the issue with photonic qubit lies in the way the two photonic qubits interact, which means entanglement or manipulation of these photonic qubits is a task, because photons, as we know, don't interact easily, unlike electrons, because they are not charged. And besides, they do not even have mass. So this is one basic flaw of photonic qubits. Then we talk of spin qubits. These include bases such as electrons and quantum dots. We talk about manipulation of these using microwaves or magnetic fields. These are compatible with silicon, and they have issues when we talk about the application. And this particular field is where I have essentially worked. The final is the topological qubits. These are also known as exotic qubits. Uh, they are sometimes known as Majorana fermions, and they are highly noise immune to noise, theoretically. And of course, the issue lies with their scalability. Currently, Microsoft is the one which is pursuing this technology, and they have come up with, I believe, an 8-qubit system only, though they are pursuing it for for a long period of time. So, having seen this, we can say that microwave lasers and probably optical fibers. These are the all the classical counterparts for realizing our quantum hardware technology. So they form the bedrock of any quantum technology. So with this, I will briefly just walk you through to the different quantum technologies. So we know the superconducting qubits. These are nothing but quantum oscillators. They are basically what? You are realizing artificial atoms. Artificial atoms. These are nothing but artificial atoms, and they are realized using something known as a Josephson junction, which basically comprises of two superconducting materials with a thin layer of insulating layer, and it allows quantum tunneling of your Cooper pair. Now, this forms a nonlinear inductor, and this, in conjunction with the capacitor, forms an artificial atom, and it gives us sorry, I made it inverse. So if you are talking about the energy structure, it is non-discrete, non-degenerate energy levels, and this makes it very interesting. So, as I said, that building of a quantum state, how your quantum states are entangled, how you are creating the superposition states, all that is quantum mechanically controlled. But if you see in this particular uh, QP architecture, where you see that these are 4 qubits, and these squiggly lines that you see are basically the ones which are helping you in the readout part or injecting signal into it. So and readout and control of these qubits is all done using these microwave oscillators. So still at the heart of this technology lies your microwave oscillator technology. So how superconducting is still closely related to electromagnetics, that is what I wanted to make it clear here. The other technology that I mentioned was optical fibers, whether it is sorry, I'm sorry. Wait, give me a second. Yeah. When it comes to optical fibers, now this technology is extensively used when we talk about quantum channels, right? That is how your quantum bits will be moving between two systems. So these quantum channels, for these quantum channels, you need optical fibers. Optical fibers, are classical waveguides, are of course controlled by Maxwell equations. Third is when you are talking about manipulation of qubits, such as the ion trap technology, the neutral vacancy centers, nitrogen vacancy centers on the neutral atoms. All these, as I just briefly showed, they are all require laser control atoms or ions. So the control and manipulation of these qubits is still done using using the classical EM theory. Now I will just briefly discuss each of this technology. So you see the superconducting quantum circuits rely on material which is cooled around 15 millikelvin technology temperature. This temperature is on almost 100 times colder than the outer space, right? At this temperature, you are basically achieving zero electrical resistance and perfect diamagnetism. Now, these materials would support quantum states where the electric current would flow without any loss of energy, because essentially you are having a zero electrical resistance, which means you will be able to the system is actually behaving like an artificial atom, and you can manipulate this artificial atom the way you want. So as I said, you will have this kind of energy diagram where one of them would be ket0 state and one of them would be a ket1 state. To move, to manipulate from 0 to 1 or 1 to 0, what you need is a microwave pulse. Sorry, an RF pulse. Which are used for qubit control and different gate operations, and also the superconducting circuits, which act as quantum memories for processors and other such requirements. So what you essentially feel is, though qubit is quantum in nature, but everything, what you are creating, what you are routing, what you are confining, and how you are measuring your microwave field, all is classical EM. So conceptually it is quantum, but physically it is still managed by EM. So EM theory is still the bedrock of quantum hardware to a large extent. The second is the laser for qubits. So in technologies like trapped ions, neutral atoms, or maybe photonic quantum computing, all of them are important, whether we are talking about how these qubits are initialized, how these qubits are, how we can change these states from ket 0 to ket 1, gate operations essentially, how your whole quantum gate structure is designed. All this operation of this, all this is done using lasers. And what are lasers? Lasers are again an application of classical EM, right? But how the lasers required for quantum technology is different from the one that is currently used in classical optics is very high precision lasers. Very high precision lasers. Because quantum by nature is so prone to noise that even a small deviation in that will lead to complete change of disaster in terms of output, right? Because we are still in that NISQ era, right? So the bottom line here is that lasers are a classical EM wave. Amplitude, phase, polarization, and frequency are engineered using Maxwell optics. But the transformations are described by certain phenomena such as the finesse of the cave or the FWHM of your laser, etc., etc. So this actually exemplifies how classical EM is still forms an important part when we talk about manipulation of your quantum states. The third important phenomenon, that is optical fibers, which are used for, in quantum bits, especially photonic quantum bits. So we are talking about a quantum network where you see, okay, these are some um, quantum repeaters, and then these are some what you call quantum computers, and then you have certain classical devices through which, I mean, somebody asked how it can be hacked or not. So all this, there's this network through which your quantum computers is manipulating it. It goes and finally reaches your classical system. So since whole network is quantum and all this interconnection is done using optical fiber. So we say that, okay, the technology here is quantum, but manipulation of this technology is still, it is still optical fibers, and optical fibers are designed using classical EM wave theory. It is still based on phenomena like total internal reflection to maintain the quantum states they carry. So again, optical fibers are a triumph of classical EM wave theory, which has engineered to preserve your quantum coherence of single photons. Any questions so far? Or should I carry on?
Please carry on, ma'am. No questions. No questions, Adi.
Okay. So next question.
Yeah, ma'am has taken a break. Just we'll wait for 1 or 2 minutes. She will join back again. Isn't it possible to hack the quantum computer by stealthily entangling qubits in future? Yeah, that's what post-quantum cryptography will be trying to do, trying to understand that if the power of quantum computing comes, how should we prepare our quantum algorithms so that there will not be any major issues. So that is the change that will be there when we come back to this aspect, right? So that's what that is this whole concept of post-quantum computing, post-quantum cryptography. We'll study that. I think it's there in QT-06 now. Post-quantum cryptography. We added a little bit on post-quantum cryptography in QT-02 also. So we'll see a little bit of introduction and overview. We'll try to give you. And I think quantum computation part QT-05, you will listen to that in detail. Ma'am has okay, give me a second. Okay, laptop charging has gone down. So ma'am is connecting the charger. So we just wait for 1 or 2 minutes. She'll join and then she'll continue. Meanwhile, I will use this time for announcements, and I think yeah, tomorrow the quiz will be open, quiz number 1, which will be comprising of classical computer and quantum computer both work in the different. Yeah, obviously it's a different aspect when you look at classical. What it can do and what quantum can do is both different. So if you simply want to understand, classical computing is basically. 1 minute. The classical computer will be like a what do you say, deterministic finite automata, and quantum computer is like a non-deterministic finite automata. That is the power which you tend to understand. For those, you can please look at theory of computation. Theory of computation, this concept is explained. Computer science faculty will know. For those who are not able to understand, maybe you can ask a computer science faculty.
I'm so sorry, my laptop.
Yeah, yeah. I was just answering few questions on your behalf.
Please carry on and give me a second.
No problem. Yeah, actually, they were wanting to ask whether classical computers and quantum computers both work in the same way, right? So that is something that we can look at. Yeah, for those who are having problems with Canvas, please wait tomorrow after the class at 5 o'clock. We'll have a presentation. We'll have a link on Google Meet and also on WebEx. Both cases we'll try to solve. So Canvas today, don't worry. Tomorrow you worry. Sunday also, if you required, we'll have a session. Right now, over to Richa ma'am to continue.
I'm so sorry for this. Great. So okay. So here we were starting with why quantum computing can be used. Quote by Richard Feynman. So Richard Feynman once said that nature is quantum, so and it cannot be simulated using classical systems. So likewise, EM, electromagnetic theory, whether it is sunlight or whether it is moonlight or whatever different phenomena that is occurring, whether it is radio frequency, whatever is happening, all these electromagnetic theory concepts are basically quantum in nature. So you cannot expect a classical system to be able to do justice when we talk about exploring the finer details of electromagnetic concepts, right? So where exactly the classical EM theory fails and how it is, how quantum is going to help in, bridging that gap is what is I will cover in this particular. So where your classical EM theory breaks down. So when we talk about dimensions as small as or smaller than 100 nanometers, which is actually the nanoscale, so what happens at this point? At this point, quantum effects become dominant, right? We are talking about electrons and photons. We are talking about how one electron is moving in a sea of electrons, right? Classically, we can, kind of simulate interaction of one electron with probably another electron. But when these two electrons is in the presence of a sea of electrons, where there are so many electrons, the way this electron is going to interact with this electron and the way this electron is going to interact with this electron is going to be different. Do you think it is possible to simulate this using classically? I don't think so. But when we talk about quantum computing technology, this can be done, right? This is one reason. The second is classically Maxwell equations do not cover the phenomena like quantized energy levels. We are, when you're talking about even softwares such as, I mean, the one that I used was numerical, and I think there are many RSoft and so many other softwares, which is this another one very famous one. I just picked this name. So all of them, the basics of solving any such equations, solving any concepts is still based on classical EM theory, classical Maxwell equation. So how can you expect something to behave quantum mechanically and in the back end you are using classical Maxwell equation to solve it? So there is another break there. And one of the most important reason is that the properties of materials are significantly different when they are at nanoscale and when they are in bulk. So, I mean, simple example is like a silver foil. A silver foil is different from a block of silver. Why? Because a very thin layer of material would, when I talk about thin layer, I'm talking about few atoms thick layer, right? I'm not talking about millions of, I'm not talking about 300, I'm not talking about microns of thickness, I'm talking about few nanometer thickness. Now this layer which is few atoms thick, it is boundary conditions here and here when they are interacting is also different. This is a thin layer stack. Now when this material is in the bulk, atom which is here, 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 they are all same except the atoms which are sitting right at the boundary, right? These are different. Why? Because these atoms which are sitting at the boundary are have different force of attraction, of different interaction with atoms sitting right next to them, as opposed to atoms sitting right next to it. So this makes it all the more complicated to use a classical EM theory for investigation of any phenomenon. Then comes the concept of quantum classical boundary I just explained. This is a boundary condition situation. So at nanoscale, the boundary condition is different, while in the bulk level, when I'm talking about bulk, I'm talking about this. At bulk, it is different. Inside the bulk, all atoms can be unified and can be, explained by a certain theory. But at the boundary level, this concept is going to be different. So when we talk about thin scale materials, thin film materials and stuff like that, you cannot use the same principles of physics there, right? Hybrid models combining the classical EM and quantum theory are necessary, but computationally intensive and challenging when you talk about implementing them with high accuracy as well as with high efficiency. Then we talk about the very famous the surface and the confinement effects. Now, this is another area where I had worked extensively: surface, plasmon resonances. So at the surface, the way electrons are behaving is very different to within this. And this is a whole field of physics known as plasmonics. Now, this is again a very quantum effect and cannot be studied using classical EM theory. Here, of course, confinement and boundary conditions at nanoscale alter the way waves propagate in ways classical theory cannot actually modulate. Sorry. Why do we need quantum computing for simulating EM? We have all the more reasons for it. Most importantly, you have a computational complexity. When we talk about problems such as this, we find a numerical methods which are currently used, such as finite discrete, finite differing time domain, or when you talk about finite effective mode, or when you talk about all these phenomena. The way you are splitting your matrix is much more dense when as compared to when you are talking about a classical phenomena. So both temporally and spatially, this matrix is going to be very, very fine. And such matrix manipulation cannot be done using the current classical models or current classical algorithms, or maybe the current classical machines. This problem actually is going to scale up exponentially and is intractable. When we talk about the quantum many body effects, and of course the electron correlation, the, the way we are talking about interactions between electron and nuclei at quantum level is way different to when we are talking about the macroscopic level. And thus, a macroscopic phenomena can be easily simulated using a classical EM theory. However, it is almost impossible to do it using a quantum mechanical phenomenon. Again, why? Because it is exponentially hard to solve this, and this problem scales up exponentially high, and currently classically it cannot be solved. Then you need for quantum mechanical descriptions, you need to study properties of nano devices, whether it is a photonic behavior, whether it is electrical conductivity or chemical reactivity, or maybe finding the ground state of an atom, or such, or things like that. Now, all these are again a quantum phenomenon, and the mathematics required for them is different altogether to what you are using a classical phenomenon. So, of course, you need a quantum system for simulating that. Then, when you're talking about studying of molecular dynamics, when you're talking about things such as quantum field theory, all this requires very accurate modeling. And essentially, the bedrock for all these is, can be solved using, again, those three magical principles: the principle of superposition, the principle of entanglement, and the principle of interference. So this becomes all the more important. Next is, why do you think quantum computers are more efficient in simulating electromagnetic interactions? First of all, because electromagnetics can be directly represented using our quantum states. You can have a quantum computer, you can have qubits with it, and these qubits can directly represent your electromagnetic theory using these quantum states, right? Why? Because these EM interactions are nothing but correlation between two waves, correlation between the electricity and magnetic field. And so it can be easily represented using a quantum mechanical phenomenon rather than a classical phenomenon. Unlike classical bits, which are just storing binary states, qubits are much easier to encode when you talk about quantum electromagnetic fields and particles. Now, mapping of these situations is helps us, avoiding the exponential memory blow up, which is, of course, cannot be handled using the classical simulations. I don't know. And I don't think so even in future you can have classical systems which will be able to handle these problems. Essentially, because as per the Moore's law, we are nearing that we are nearing that point where classical systems cannot become smaller than what it actually is. There is a certain limitation to classical computing in terms of hardware. So yes, there is this limitation here. Another interesting principle is that what we talk about all the time is superposition and parallelism. So quantum superposition allows you a quantum computer which can process multiple possible outcomes simultaneously, right? Now, and this particular parallelism will help you simulate electromagnetic phenomena, which is exponentially large in a big solution space, and yet it can be done using a quantum computer, which is, of course, not possible using classical systems, even using brute force methods. And then, as I mentioned, there is a certain correlation between electromagnetic quantum systems, and this can be done using quantum principles, quantum mechanical principles. And whether it is encoding of this qubit or whether it is implementation of the correlation, all this can be done using quantum entanglement. And thus, when we talk about principles such as prediction or optimization of a certain EM systems, it can be easily done using your oh, sorry. What happened? I'm sorry. Give me a second, please. Why is this happening? Am I audible?
Yes, ma'am.
I'm so sorry. I think there's certain issue around this.
No, now it's okay, ma'am. Audio is fine.
Okay. I'm sorry. In case if it God. I'll share my PPT from here itself.
Yes. Okay.
Right? I think there's certain issue around that. What happened? I think I discussed this.
Screen is not yet shared, ma'am.
Oh, sorry. Wait. I'm sorry. Can you see my screen?
Yes.
Okay.
Yeah.
You can see this.
Yes.
I think I have to stop using the use of iPad. I will do directly here. I'll just try my best.
Yes.
And thanks for this adjustment with me. I think I had done this. Okay. So here is a small example of how we can use quantum systems for realizing one particular problem. Supposedly, I have to realize. Let me see if there's a laser pointer here. How do I see a laser pointer? Laser pointer. Okay. Can you see the laser pointer, all of you? Is a laser pointer visible? Am I audible?
Yes, ma'am.
Okay, great. And the laser pointer is visible, right? The laser pointer.
1 minute.
Can you see this dot? Okay, good.
Yeah. Dot.
So now,
Yes. Red dot.
yeah. Now I will basically take a simple example where you will see how we can kind of simulate strongly coupled quantum field theories using quantum simulation, right? So what is the whole idea? So quantum field theories are classically intractable problems, and you cannot you cannot simulate these quantum field theories using the classical model. So what do you do? I mean, in terms of quantum computing, you first build up the Hamiltonian, right? And in principle, under normal conditions or classical conditions, you know that opposite charges repel each other, while under quantum conditions, it is possible that opposite charges repel each other. Now, this kind of phenomena cannot be exploited or studied or understood using a classical theory. So, what you need is a quantum theory. So, you first write the Hamiltonian for it, and once your Hamiltonian is ready, you do the realization of this using a quantum computing algorithm. Now, this algorithm would be a special algorithm which is designed under such boundary conditions which would satisfy all your quantum field theory concepts. Now, once this is run, once this is executed, it will help you understand how quantum field theory is going to explain, give you a deeper insight into different natural phenomena, physics from the physical aspects, from biological aspects, or how time can evolve over how time can evolve. Right? Imagine we had a Big Bang theory and how time would evolve, and how all this phenomena can be basically studied using concepts of quantum field theory. And quantum field theory can be simulated using something called a quantum computer. So this is just a tiny example of how how this can be useful there. Now we talk about the different quantum algorithms which could be useful. So remember the different stacks we talk about, the different layers of quantum system, right? We talk about the physical aspect, we talk about the error correction aspect, and then on top of it was sitting a quantum algorithm. So if you have to realize any problem, you should have the mathematics for it, right? And what is mathematics? Mathematics is nothing but algorithm. So any problem that you have can be explained using something called an algorithm, and the language that a quantum any algorithm understands is a language of mathematics. And Dr. Rahman, I am pretty sure, did justice to that particular field, where he would have tried to understand, try to explain you how mathematics and quantum computing are interrelated. So now here I will briefly walk you through the different algorithms which are available. Now these algorithms, some of them are just theoretically available, and some of them are actually implemented. So on top of the list appears this particular algorithm called the variational quantum algorithms. Now, these are algorithms which are basically written for the NISQ era. NISQ, if you remember, is I had acronymed it as Noisy Intermediate Scale Quantum Era. Now, this is the era where we are actually living, and I explained you the concept of physical qubits and logical qubits to the same. So this is the era where your quantum bits are still prone to error. So if you're in such an era, you cannot imagine solving a problem which requires thousands of qubits, right? So your problem statement is fixed. You have a fixed quantum hardware. When I talk about a fixed quantum hardware, I talk about both in terms of the number of qubits that are available, the speed at which this quantum hardware is working, and the number of operations this quantum hardware can do in one shot. Right? So keeping all this into I mean, so you see, you have so many limitations. You have limitation in terms of the noise. You have limitation in terms of the coherence time. You have limitation in terms of the qubits. You have limitation in terms of the clarity of the output that you get. Right? With all these limitations, what best could be achieved is a hybrid quantum classical algorithm, which means you put some parameters into this quantum circuit, run this on the basis of these parameters, you do your manipulation, you run your circuit, you get your output, Now this output is classical. Now on the basis of this output, you do some simulations. Now once you get the output, now this system is classical. Now your classical system is going to work on this output and try to find out how good is this output. Now if you say, okay, now your output was supposed to be, say, 2.5, and the output you're getting is 2. So you need to, get your output better. So now you reparameterize it. So your classical system is going to readjust the parameter. Once the parameter is readjusted, it again does that quantum calculation and throws out a result which is classical. This classical results goes into your classical machine, and the classical machine post processes it and understands how good is your result. So this type of system where both the quantum and the classical processing is happening in tandem is a very good example of a variational quantum algorithms. And this is the phase where we are actually is. And these algorithms are used to simulate complex materials, electromagnetic interactions, etc., etc. They can be used for modeling wave propagation, for material responses, in electromagnetic interactions, etc. The next set of algorithms is quantum phase estimation algorithm. These algorithms are still in the theoretical phase, and they can be used to solve eigenvalue unitary operators, which can be explained using Maxwell equation, and can be used to solve electromagnetic systems with very high precision. The most important application of quantum phase estimation lies in solving quantum chemistry problems, inventing, discovering new materials, and extending this to electromagnetic field problems. The third is a quantum Hamiltonian simulation. Now, in this case, you build up a Hamiltonian, and based on these Hamiltonians, you are having special algorithms to solve these Hamiltonians, right? And these Hamiltonians are built, these are governed by your electromagnetic phenomena. And then you can use them for implementing techniques such as Trotter-Suzuki decompositions. You can do embedding, you can do qubitization, and then allow efficient simulation of Maxwell equations using these Hamiltonians that you have built up. Again, this kind of set of algorithms is still in its theoretical form because current hardware does not support them. Then there is this quantum Gibbs sampling phenomena, in which you are sampling some complex probability distributions, and you are trying to solve various thermal and equilibrium properties of EM systems, and they can basically help in the precision of statistical modeling as well as machine learning on the electromagnetic data available. Again, this is in a theoretical form. Quantum machine learning is something which is very popular amongst researchers. And in this case, we are basically leveraging the quantum enhanced linear algebra routines, the matrix inversion, principal component analysis. And these principles are basically used for, modeling the various electromagnetic data. And once your data is ready, you can encode this, embed them, and then you can learn and predict electromagnetic material behaviors faster than your classical methods. And you can accelerate the design and optimization also. Another set of algorithms are the feedback-based quantum algorithms. Now, they are basically dynamically adjusting the quantum circuit parameters and then basically using it for different optimization problem and stuff like that, and has been demonstrated by MIT and stuff. Again, these kind of algorithms are still in their developmental stage. With this, I will just give you a brief example of how variational quantum algorithms are important and which fields they are important. So variational quantum algorithms, as I mentioned, are useful when we talk about machine learning objectives. They can be used for error correction technologies. Somebody had asked that on what algorithms error correction would be based. So variational quantum algorithms is the answer to that. They can be used for solving combinatorial optimization problem, and these set of algorithms are known as QAOA, quantum approximate optimization algorithms. Then VQAs can be used for solving mathematical applications such as factoring very large numbers, and essentially when we talk about RSA encryption and stuff like that, cryptography essentially. And then there is this whole range of problems called as quantum chemistry, which is um, which is basically dedicated to simulation of quantum simulation of atoms, a ground state of atoms, which can eventually be used for various applications, whether it is related to drug discovery, whether it is related to new material invention or stuff, so on and so on. And finally, we have a whole range where we talk about dynamical simulations. In this particular field, here we talk about time related, how time would evolve in under certain conditions. So these are dynamical simulation problems. So here we see how variation quantum algorithms has actually made a mark in this particular field, and yeah, how variation quantum algorithms are important. Here in this particular zone, here we talk about how discovering of new algorithms is important to the whole technology. So you discover new algorithms. Using new algorithms, you do some good simulations. Using good simulations, you will come up with new materials, and using new materials, you can again come up with a new hardware. And then, of course, this is a whole loop of such structures. So I would like to stop here and would like to take questions from the audience. Thank you for this time of yours, and go ahead with your questions, please. I have a whole another slide deck, but again, that will take another 40-50 minutes. So if you recommend, I can stop here and I can take questions. The other slide deck is basically talking about challenges and what are the limitations and what are the quantum breakthroughs required and what are the software innovations required here.
We'll take a break here, ma'am, and I think I'll see if I can put 1 more hour somewhere for you. At that time, we'll discuss the challenges towards the end of the course, maybe.
Yeah,
The last part,
yeah.
we can, when the
Because
challenges are
I will
discussed or
definitely
applications.
share this slide deck. It is a very theoretical concept. Probably people can just read through it and would understand. It is something not very, I would say, I mean, it's something that people can understand.
You can read through, yeah.
Yeah,
You
yeah.
can understand on
It's a very theoretical concept. So whatever
some of these things are interest to me because I teach hardware. I want to teach hardware because that is one thing that India needs. So yes,
absolutely.
yeah. Few questions, ma'am. Why cryogenic coding is challenging in quantum computing?
Why? Which coding?
Cryogenic cooling.
Okay, cryogenic cooling is crucial. See, quantum, as the word says, it is um, it is susceptible to noise. So what happens whenever you have a rise in temperature? You know, electrons start moving, particles around you would start moving crazily, right? And you don't want that to happen, right? You want some kind of I would say some kind of stability there when it comes to the basically high temperature means high noise, and noise is something that you cannot basically play with. I will stop sharing, I think. Right? Am I audible?
Yes, ma'am.
Okay, okay. Okay.
Yeah, NFA and DFA are equivalent in power. I was discussing that before you came. So actually, yeah, that's what when you do measurement, the NFA becomes equivalent to DFA. So that's the quantum and classical. You can read a little bit about it.
I'll do
Another
that.
question. Yeah. Madam has told that Microsoft has used topology for qubits,
Yes.
and they are claiming a fourth state. If you have some
Claiming a
information, kindly. Claiming a fourth state.
fourth state. No, they talk about Majorana fermions. So fermions, Majorana fermions, how they have explained it beautifully using glove and sock example. So gloves are is interchangeable, is not interchangeable, right? A right hand would wear a right glove and a left hand would wear a left glove. While 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 a sock can be is interchangeable, any foot can wear any this. So major a fermion is like a sock, and otherwise a fermion is like a normal fermions is like a glove. So these are antiparticles of itself. A fourth
Right.
state, by fourth state, they are actually talking about the fermionic state in which they have created this kind of state.
Yeah. I would encourage you to read a white paper on Majorana, Majorana 1, Majorana 2. You will be able to get that, right? Majorana, I'm not sure. Yeah.
Some people call it
Ma'am, can you
nano-
explain?
yeah. Sorry.
Yeah, some use either. Can you explain nanoscale dimension with an example where classical laws are not applicable? Nanoscale
Example
dimension,
there. Okay, I'm seeing the question.
where classical laws are not applicable.
Okay, you are talking about nanoscale. See, in when you talk about nanoscale, I'm basically talking about few atoms thick. Now, when you go to a level as small as an atom, right? When you go to that scale, classical will not hold at all, because classical, as per classical laws, you have to follow Newtonian's principles, right? When you cannot explain phenomena like as quantum tunneling. So in order to explain phenomena such as quantum tunneling, you have to your particle, you are basically dealing with the nanoscale dimensions, and thus you cannot explain your quantum concepts like quantum tunneling, concepts like interference or superposition. You will not see in a classical world two particles getting superposition. You cannot imagine your cup to be, i mean you can see your bottle here, right? So you cannot imagine your bottle to be here and in America at the same time. Your bottle is there, it's there. You cannot imagine it to be at two places simultaneously. So in classical world, we don't have phenomena like this. When we talk about nanoscale dimensions, in a nanoscale dimensions, supposedly we're talking about simply a structure of atom. And in electron, you can imagine, okay, there's a whole cloud of electron, and there's a certain probability that your electron is there. You don't say with 100% guarantee that okay your electron is going to be there. You say there's a certain probability that your electron is in somewhere in that electron cloud. So that is how you explain. You cannot explain nanoscale phenomena using a classical law.
Yeah. Last question, madam. How quantum phenomenon is compatible between EM, electromagnetics, and optics?
How classical? Sorry.
How quantum phenomenon is
Okay.
compatible between electromagnetics and optics?
Well, optics is what, as I mentioned, optics came under the umbrella of electricity and magnetism and electromagnetism phenomena. So uh, of course optics, I mean optics also, there are two fields of optics. If I have to explain it, there's something called quantum optics, and there's another something which is called the classical optics. Classical optics is where we are just talking about light as a wave, and when we talk about quantum optics, we talk about optics as particle in nature. So there is this optics where we talk about light as photons, and there's another optics where we talk about light as wave. So there is a certain continuous spectra of light, and there's another optics where we talk about E is equal to h nu, if that makes it clear. Any other question?
Yeah, I think that was the last. Okay. Is there any window in temperature range, error in temperature to get qubits in superconductor qubits?
Okay, normally it is the temperature is maintained around 15 millikelvin, as I initially mentioned. So, and this temperature that somebody that has been calculated depends upon the radio frequency pulses or the microwave pulses, which are helping in control and readout of the signals. I don't. I mean, plus minus 5 Kelvin, 5 millikelvin could be a solution to it, to the answer to this. Honestly, I don't know,
Okay.
because even a
Yeah.
slight change in temperature would affect the coherent state of your qubits. So they would like to maintain it as close as to this. So having said that, I will also tell you this is a very interesting thing here is also that how to measure, how to sense temperature as low as this. So the whole technology of a cryosystem is not just building this dilution refrigerator, it is also how you are sensing this, such low pressure, such low temperatures. The uh, the whole the whole aspect or the whole technology behind this is also very interesting to study and to understand.
Yes, ma'am. I think the questions are done. Yeah.
Great.
Why are we using different qubits?
Different qubits, I think by different qubits, you mean the different qubit technology, right? Okay,
Yeah, I
now,
think.
unlike the classical computing where it has, I would say, matured to this level that we have one common platform in which all of us are using the same semicon technology, and essentially how you are coming up with maybe fabrication of a transistor or whatever is generalized, right? It's not like that Intel is using a different technology, or maybe ST is using different. All of them are using almost the same technology. How you are scaling it is perhaps each of the companies, um, I would say, the business point. But when it comes to quantum technology is at a very very initial stage. It is right at a very precipice of it is where super transistors was in 1950s. So right now quantum technology is there. So no technology has been is a clear winner, because as I showed you on that slide show, each technology has few pros, few cons. And there are few technologies which are being commercially implemented. There are other technologies which are not commercially a success because of various reasons, right? uh, Maybe scalability, or maybe fabrication, or maybe implementation, whatever. So we are still in that experimental phase, and everybody, whoever, like IBM is saying superconducting, and we say, okay, this is the technology of the future. Or maybe Ion Q is saying, okay, trapped ion is the best technology. Maybe Xanadu is claiming that photonics is, because no, right now we don't have logical qubits. We don't know. Nobody has come up. People are claiming, okay, this is how it's going to scale up. We will have million of qubits. We will have thousands of qubits. We'll have million of qubits. We'll have error correction. But nobody is there at the moment. So it's an experimental stage. That's all what I can say about it. Give some real life examples of quantum entanglement. By real life example, you mean, I mean, this is what is actually used in photonic qubit systems when we talk of quantum telecommunication. So this is what is actually used, if that is what you mean. I hope I was able to communicate uh, the crux of this session, and it was completely a pleasure teaching you. Of course, the questions were very intuitive, and of course, I like the spirit. I thought that most people must have slept through the course, but I'm happy that people are still awake. Thank you for your
Yes,
time.
yes. Actually, yeah, they know the value of especially people like you coming and sharing, and also they are taking very seriously. I think
Yeah, yeah, I
both
can
the courses
understand with
that
the
you
depth of the
present.
questions.
Yeah,
I'm
yeah,
pretty sure that
and they're following and they're thinking also.
that's
So
important.
that's very there may be some who are struggling. For those who are struggling, please bear. I just say
Not
please
with
hold
them.
on, right?
Just hold
Because
on.
some of the concepts are coming, they are reinforcing. As madam has already told you, many things, the reinforcement also is being done. Slowly, slowly, things are getting clear for you. And as you hear more of these terms, more clarity will come. So please just hold on. There are faculty from economics, from commerce, and other streams also. Maths, physics, and electronics in computer science, the faculty will find it very easy. Maybe agriculture, especially the statistics part, some of them may find it comfortable. But others who are from totally unrelated fields, especially non-engineering and non-science, it will take some time. and everybody can learn. I know many of my friends who learned IBM mainframe just like that without having any knowledge on computers. And they are now architects, software architects, many of them. So in that similar sense, please hold on. You may be a master of quantum in no time, right? Just hold on
Just hold on.
and
And
go through these courses.
just to say
Yeah.
that me and Dr. Rahman will be soon coming up with a book based on quantum computing. So it's going to be kind of a layman guide for all of you. And once it is out, of course, we'll put it on the LinkedIn thing, and you can just, I mean, you can read through it. Maybe it might help you, strengthening your strengthening your knowledge on in this particular era.
Yeah, mostly it has been written. What I gather from Rahman and ma'am is that it has been written from a layman perspective, that somebody who doesn't know, try to understand and slowly build the concept. So that's what we are doing. Please wait. Quantum technology and application concepts will start. Then quantum computation and concepts will start. So by the time QT-0001 is completed, then you decide whether okay, quantum is not for me or quantum is for me, right? So don't lose heart. Please bear with this course. Of course, the faculty who are also coming. They're coming with a lot of willingness to share a lot of things. So that's also sometimes, if we tell something, very few things, and leave you, you may feel very comfortable. But actually, 2 hours they want to give so much. You can see the amount of preparation that Rahman sir and Richa ma'am have put in. Thank you so much, ma'am. We will hear more of you. And ma'am is taking few lectures in QT-06, and also QT-07 is a specialization sensing. Then also in materials, also QT-08, she will be speaking. Some of these concepts she will be elaborating. Hopefully, we will meet her soon. And of course, in the subsequent sessions also, whichever topic she finds it comfortable, she will be there. Hope you have enjoyed, and you could also feel the way that her PhD is from a reputed institute and also working in IBM. The way that they presented, that is really, we must learn as teachers. They are interested in, as a passionate to be teaching. So I think we should also pick up some of these things from her. Thank you so much, ma'am. Thank you all participants.
And thanks for giving me this opportunity.
Yeah, PPT ma'am will share, and I will immediately upload on Canvas. So we will share it to you. And tomorrow evening, the quiz will start. So don't worry, you will have time till Monday evening to take the quiz. But you will have to attend tomorrow at 5 o'clock. We'll do a refresher session for those who have not joined Canvas. So be tuned in. Richa ma'am, please send few questions as well from the topic that you have just covered, maybe 2 or 3 or 4 or 5, whatever, right? Ramsey has already sent. Maybe 1 or 2 you can send, 3 or 4.
It's a pain. I mean, asking questions,
Yeah.
it brings me back some bad memories.
Right. Yeah. So maybe multiple choice actually. So you can send that. Yeah, sure. Thank you, ma'am.
Thank you so much.
Thank you once again. And yeah, you can see the appreciation in the chat. So yeah. Thank you. Thank you, ma'am.
I was really happy with the questions that came up. Thank you.
Thank you.